Welcome back to ECE 442-542. We are now finishing up our pieces that make up lecture 5.2, and this one is really just a summary of the performance specifications for second order Z-plane pole locations. Let's just quickly review what we've already learned or determined. If we now have a settling time specification, then that corresponds to circles in the Z-plane, and this 1% settling time gives us the relationship or equation, the radius r raised to the power n sub s, where n sub s is the number of steps to get to the 1% value in a settling time behavior, or in this exponential decay. Then we can use that to actually derive the relationship between R and T settle, where T settle now is in terms of the number of sample periods or the number of steps to reach the settling time. So if somebody gives you T settle, or they give you the number of steps or sample periods in the 1% settling time length, which is n sub s, T sub settle now is n sub s t, n sub s is T settle over T, and we can now rewrite or express the radius that those poles need to be at in order to achieve that settling time. The radius is 10 raised to the minus quantity 2 over n sub s. Likewise, if somebody now says, oh, here are your poles and they're this far away from the origin in the Z-plane, what's my settling time? Well, you can resolve or solve for A's answer in terms of n sub s, and now this is the ceiling function, which corresponds to the smallest integer just above this numerical value inside the ceiling function brackets. So now if somebody gives you R, you can compute the number of samples that corresponds to relative to a settling time in the Z-plane. And remember, R for settling time, the radius has to be inside the unit circle. So R needs to be less than 1. For percent overshoot, that's the zeta value, and that's our heart shapes. If somebody now gives you a percent overshoot specification, you can use this relationship or this formula to solve for zeta. And once you're given zeta, or if you're given zeta, you can now solve for the percent overshoot, which is 100 e to the minus zeta pi over square root of 1 minus zeta squared. So depending on what somebody gives you, either percent overshoot, you can solve for zeta, or if they give you zeta, the damping ratio, you can tell them what the percent overshoot is going to be. And that corresponds to a particular logarithmic spiral in the complex Z-plane, where zeta equal to 0 corresponds to the unit circle, and zeta equal to 1 makes or corresponds to poles being on the positive real axis in the Z-plane between 0 and 1. The peak time is our wedge shape, or it's these angles. Time to peak is pi over omega sub d, and the angle that these closed loop poles make in the complex Z-plane is given by theta sub d, which is omega sub dt. So omega sub d is now equal to theta sub d over t. We can use that in our time to peak expression to eliminate omega sub d, and now you have time to peak in terms of angle theta sub d and the sample period capital T. So time to peak is now pi t over theta sub d. If you're given a time to peak, let's say time to peak is so many samples, capital N sub p, you can solve N sub p is equal to time to peak over t, and now you can use that in this relationship for theta sub d. We know time to peak is n sub pt. We know n sub p is T sub p over capital T, and you can substitute in for T sub p and find this relationship between theta sub d and n sub p being theta sub d is equal to pi over n sub p. Likewise, if somebody gives you theta sub d, you can now either provide them with the time to peak in absolute sense, or you can express that in terms of the number of samples to get to the peak. Remember, T sub p can be parameterized in terms of n sub p as n sub p capital T. So now we just cancel out the t's and we see that n sub p is pi over theta sub d. We can now put all of that together to produce a performance specification table where, given certain combinations of design specs or performance specs, two of these parameters, either t-settle, percent overshoot, or time to peak, you can now express the z-plane pole locations corresponding to those specifications in terms of either r and zeta, or r and theta sub d, or zeta and theta sub d. So the only real hard ones are when you now have something other than r and theta sub d. If somebody gives you r and theta sub d, they've given you the polar form of those z-plane pole locations. So if they give you settling time and peak time, you now can immediately write down where those closed loop poles need to be. Likewise, if they give you r or t-settle and percent overshoot, they're giving you r and zeta. You can now find r and theta sub d. R was determined by t-settle. Theta sub d, which we derived in an earlier lecture or segment of this lecture, is minus natural log of r over zeta times the square root of 1 minus zeta squared. If they give you zeta and theta sub d, you can now derive the radius expression in terms of zeta and theta sub d, so that you don't need to explicitly have r, but now you have it indirectly in terms of zeta and theta sub d. This performance table then is very helpful in translating these particular design specifications into closed loop pole locations in the complex z-plane.